Good morning, all of you. Yesterday, we stopped with Coulomb's law. And Coulomb's law is the method to find out the force between two charges separated by a distance. And if the charges are separated in free space, equation for finding the force between them using Coulomb's law is 1 by 4 pi epsilon 0 q1 q2 divided by r square. And I told you epsilon 0 is the permittivity of free space. And if the charges are present in any kind of medium instead of free space, that epsilon 0 can be changed into epsilon. Epsilon is the permittivity of the medium in which that charges are present. So epsilon 0 has its own value. Epsilon 0 is the permittivity of free space. It has a particular value. And its value is 8.85 into 10 to the power minus 12. 8.85 numerical value is 8.85 into 10 to the power minus 12. And when you are substituting that 8.85 into 10 to the power minus 12 in that constant 1 by 4 pi epsilon 0, you can calculate it. You know, value of 4 is 4 itself, and pi is 3.14, and now epsilon 0 is 8.85 into 10 to the power minus 12. Then if you are substituting this value, you can find it as 9 into 10 to the power 9. So if it is 9 into 10 to the power 9, then that equation for finding the force between two charges separated by a distance r in free space becomes F is equal to 9 into 10 to the power 9 q1 q2 divided by r square. So it's very simple if it is present in free space. But when it is present in any kind of medium, then what to do? You have to substitute epsilon 0 with value of epsilon for that particular medium. For different medium, value of epsilon will be different. So in generally, if you are talking about the charges present in free space, you can use, instead of 1 by 4 pi epsilon 0, you can use 9 into 10 to the power 9. So Coulomb's law is an easy method to find out the force between two charges when they are separated by a distance. Okay, so that is Coulomb's law. When we are talking about Coulomb's law is a method to find out the force between two charges. You know, force is a vector quantity. So if you are talking about a vector quantity, you have to define its magnitude as well as direction. So magnitude is given by Coulomb's law, but how you can find its direction? That is a question. So we have gravitational force, and that gravitational force is acting along the line joining that two masses. Similarly, Coulomb's law acts along the line joining the two charges. So if you are having two charges q1 and q2 separated by a distance r, so you can see that q1 will experience a force due to q2 and q2 will experience a force due to q1. And the force between, if you are considering the value of force acting on q1 due to q2, you can express it as F12. I think you can see it. F12 is equal to K into q1 q2 divided by r square multiplied by unit vector r12. What is unit vector? You know that it's a vector having magnitude 1 and acting in a particular direction. And what is the direction here? It is a line joining q1 and q2. R12 is the line joining q1 and q2. So we can see that in full sense with magnitude and direction, the force on q1 due to q2 can be expressed as F12 is equal to K into q1 q2 divided by r square multiplied by unit vector r12. Is it clear? I think it is clear. So when we are talking about the force on q2 on q1, that means the force acting on q2 due to q1, that force you can express as F21. How you can express that F21? F21 is equal to force F21 is equal to K into Q2 into Q1 divided by R21 square multiplied by unit vector R21. You can compare with the force F12, and you know F12 you have written as K into Q1 Q2 divided by R12 into unit vector R12. Here force is acting on second charge Q2 due to Q1. So you can express it as F21, and which is equal to K into Q2 into Q1 divided by R21 multiplied by unit vector R21. That is the vector representation of Coulomb force. Coulomb force, you know, that is the force between two charges. So this expression completely defines the force between two charges. So that is the vectorial representation of Coulomb's law, or the vector representation of Coulomb's law. So that completes the description on Coulomb's law. So Coulomb's law defines the force between two charges, and the direction of the force is given by unit vector acting along the line joining those two charges. Is it clear? I think so. Okay, so when we are talking about two charges and similar charges or opposite charges, if they come close to each other, there should be a interaction. There should be an interaction between these two, which means either they will attract or they will repel. Anyhow, they have to interact with each other. So how these charges are interacting, since they are not come in direct contact? Even though they are not coming into direct contact, they can influence the other charge. How it is possible? That is an interesting fact. Even though they are not coming contact, they can interact each other. So you know, in physical world there are different kinds of forces, contact forces and non-contact forces. So this Coulomb force can be considered as a non-contact force. Why it is called a non-contact force? Because that force of attraction or repulsion between the charges is not due to the direct contact between the charges. Even though they are not coming in direct contact, they can interact with each other. That is why it is called a non-contact force. So how these non-contact forces can act? For that, you can consider a particular charge, and when you consider that particular charge, you can find a region surrounding that charge through which we can feel the effect of that particular charge. How you can find the effect of, or how you can feel the effect of a charge? Suppose you are having a positive charge, and when you are bringing another positive charge near to that particular charge, what will happen? It will get repelled. And if you are bringing a negative charge towards that particular charge, what will happen? That charge will get attracted. But you can't feel that repulsion or attraction at a large distance from that particular source charge. We can have two kinds of charges in this description. One is the source charge and the other is the test charge. So the source charge is the charge already present there, and the test charge that you are taking for your convenience for any kind of studies. So here you can have a source charge, suppose Q0, capital Q0 is the source charge present somewhere, and you are bringing a small letter q charge, that means small q charge, amount of charge near to that Q0. Suppose both are positive charges, that means Q0, that means capital Q0, our source charge is also positive charge and your test charge is also positive. So if you are bringing that Q0 from a larger distance towards our source charge, initially you are not feeling any force of repulsion. But when you are bringing that charge, test charge, near to the source charge within a particular distance, then you can slowly feel some repulsive force. As you move towards closer to the source charge, that repulsive force will increase, which means the effect of that source charge is very much strong when you are very close to that source charge. As you move away from the source charge, its effect is going on decreasing. So you can define a region surrounding a particular charge. In this case, you can have our source charge, and you can define a region surrounding that source charge through which only you can interact with that charge, which means if your test charge is inside that particular region, then only these two charges can interact. So for every charge, there should be a region surrounding that particular charge through which only it can interact with another charges. And that particular region is known as electric field. That particular region is known as electric field. Please note down, electric field is a region surrounding a particular charge through which only it can interact with another charges. Is it clear? It is very similar to your gravitational field. Last year we have talked about gravitational field. Gravitational field is the region surrounding a mass through which only it can interact with another masses. Similarly, here you can have the electric field. Electric field is the region surrounding a charge through which only it can interact with another charges. So when you are talking about an electric field, we can't say that surrounding a charge, a particular charge, there should be a continuous region through which it can interact with another charges. It's not so. Gravitational field is a continuous one, but this electric field is not so continuous. That means electric field is distributed only through certain regions. How you can find it out? Which means suppose you are surrounding a region surround a source charge, and when you are keeping a charge but at a particular point inside it, sometimes it will not feel any repulsion or attraction depending upon the nature of the charges, which means electric field is not continuous. Electric field is acting only through certain lines, and those lines are called electric field lines or electric lines of force. Why it is called electric lines of force? Because even though inside the electric field, electric force is experienced only through that certain particular path. So electric force is experienced through certain path in an electric field, and those particular paths through which only electric force can act, that region or that lines or that paths are called electric lines of force. Can you get me? So when you are talking about a positive charge, if you are bringing another positive charge to very near to that source charge, it may get repelled, but it is not getting repelled in any direction from that particular source charge. I will show you how these electric field lines are acting. So you can find some slides here for which electric field lines are acting. See, here you can see electric field lines. So from a positive charge, these electric field lines are diverging, and to a negative charge, that field lines are converging into. From the positive charge, they are diverging, and from the negative charge, they are converging into that negative charge. So how you can define these electric lines of force? And electric lines of force are different for positive charge and negative charge, different in terms of its direction. So how you can define electric lines of force or electric field lines? So electric field lines, you can define the path through which a unit positive charge can travel when it is placed in an electric field. Are you getting? Electric field lines are the paths along which a unit positive charge can travel when it is placed in an electric field. Now you think about what kind of forces are acting on a unit positive charge when it is placed near to a positive charge or near to a negative charge. Obviously, when it is placed near to a positive charge, it will get repelled. Repelled means the test charge is moving away from the source charge. So, when the source charge is positive, electric force is acting on a unit positive test charge away from the source charge. That is why electric field lines are diverging from a positive source charge. Are you getting? A unit positive charge, when it is placed near to a negative charge, what will happen? It may get attracted towards the negative charge. So, electric force is acting towards the negative charge on a unit positive test charge. That is why for a negative charge, the field lines are converging into that negative charge. Now I think you are getting the direction of electric field lines for a positive charge and a negative charge. Is it okay? Okay, so when you are considering a positive charge, electric field lines are diverging from positive charge and converging into a negative charge. Diverging from positive charge and converging into negative charge. I repeat, electric field lines are the path along which a free unit positive charge can travel when it is placed in an electric field. So, electric field lines are present only in electric fields. Electric field lines are present only in electric fields. So, it is the path of a unit positive charge when it is placed in that particular electric field. If it is a positive electric field, that means electric field of a positive charge, electric field lines are diverging out, and if it is placed in a negative electric field, that means electric field of a negative charge, it will converging into that negative. Okay, so that is electric field and electric field lines. So electric field is a region surrounding a charge through which only it can interact with other charges. And this electric force of repulsion or attraction is distributed only along through certain paths in an electric field, and those paths are called electric field lines. Okay, so now we are familiar with what is charge, how charge can be acquired, and how charges can interact, and how you can find out the interaction between two charges. Now, how these non-contact charge interactions are possible, that are due to, or that is due to electric fields, and how these electric fields are distributed surrounding a particular charge. Okay. Okay, so when we are talking about electric field lines, these electric field lines have some special properties that are the characteristics of electric field lines. Characteristics of electric field lines. So please note down when I am talking about these properties of electric field lines. The first property is electric field lines starting from positive charge and ending in negative charge. We have already explained it. Electric field lines starting from positive charge and ending in negative charge. They diverge from positive charge and converge into negative charge. And second property is they are unidirectional. Electric field lines are unidirectional, which means at a particular point in the electric field, it has only one direction. At a particular point, it has only one direction in an electric field. So, electric field lines are unidirectional. That is the second property. And the third property is electric field lines never intersect. Electric field lines never intersect. They do not cross each other. What may be the reason? If they are intersecting each other, at the point of intersection, they can have two directions. Is it? When two lines are intersecting at the point of intersection, there are two directions. So, when two electric field lines are intersecting, it is against your second property. What is second property? Second property says they are unidirectional. So, when two electric field lines intersect, it is against your second property. So, third property of electric field lines is electric field lines never intersect. Okay. And another property of electric field lines is, I told you about the electric field, and strength of electric field is directly proportional to the number of electric field lines. Are you getting? Strength of electric field, that is electric field intensity. We will come to that topic later. Anyhow, the strength of electric field is directly proportional to the number of electric field lines. Which means in an electric field, suppose you consider an electric field and you consider a particular region, and in that particular region, the number of electric field passing through that particular region is suppose 25. Just a number, 25 electric field lines are passing through that region. And you are taking another region which is very close to that charge. And when you consider another region surrounding the same area, similar area, you are taking very close to that source charge. And you are finding the total number of field lines passing through that particular region. And you are finding that is 100 field lines are passing through that particular region. In the first region, 25, in the second region, 100 field lines are passing. And the first region is somewhat away from the source charge, and second region is somewhat closer to that source charge. Can you imagine where will be the electric field intensity is more? That we have already seen. When you are coming close to the source charge, the electric field strength will be more. Obviously, in the second region, the electric field intensity will be more. And you can find that there the number of electric field lines is also more. So there is a direct proportionality between electric field intensity, that means the strength of electric field, and the number of electric field lines. So we can see that electric field intensity is more where the number of electric field lines is more. So that is another property, fourth property. That means the strength of electric field is directly proportional to the number of electric field lines. And another property of electric field lines is electric field lines are parallel in a uniform electric field. What do you mean by uniform electric field? Uniform electric field is the electric field where electric field intensity, that is the strength of electric field, is same everywhere. That means wherever you are considering all the points in that particular electric field, the electric field intensity will be same. Some kind of that kind of regions or that kind of electric fields are known as uniform electric field, which means the electric field, electric fields where the field intensity remains constant throughout. So in a particular, in a electric field, in uniform electric field lines are parallel to each other. Electric field lines are parallel to each other. So the properties of electric field lines are, they are starting from positive charge and ending in negative charge. They are unidirectional and they will not cross each other. Electric field intensity is directly proportional to the number of electric field lines passing through that particular region. Then in a uniform electric field, the electric field lines are parallel to each other. Okay, so that are the properties of electric field lines. So I repeat, electric field lines are the regions or the path through which a unit positive charge can travel through in a particular electric field. Their properties are, they are starting from positive charge and ending in negative charge. They are unidirectional and they will not cross each other. Then in a uniform electric field, they are parallel to each other, and when we are talking about the electric field lines, the number of electric field lines is directly proportional to the electric field intensity. Okay, so when we are coming back to our electric field, that is the region surrounding an electric charge through which only it can interact with another charges. The region through which only it can interact with another charges. And we have seen during this small description, the electric force acting on a test charge present in an electric field is not uniform everywhere. Which means if the test charge is very close to the source charge, it will experience more force, whether it is attractive or repulsive, no problem. And if the test charge is moving away from the source charge, then the interaction will be less. Okay, so the strength of electric field is not equal in all the electric field. Some exceptions are there that I already told you, uniform electric fields. But generally, if you are talking about a source charge, its electric field is not uniform. When we are keeping closer to test charge, closer to the source charge, it will feel more interaction, repulsive force if the test charge and source charge both are having the same nature. And if the test charge is taken away, that means at a far distance from the source charge, then the interaction will be less. So we can generally define the strength of a electric field. The strength of electric field at a particular point, that is known as electric field intensity. So electric field intensity, how you can find out the electric field intensity? How you can find out the electric field intensity at a particular point? Remember, electric field intensity is the property of that particular point in an electric field. In a non-uniform electric field, when that point changes, electric field intensity is changing by point to point. Electric field intensity is changing from point to point. So how you can find out the electric field intensity at a particular point? or how you can define the electric field intensity at a particular point. For finding the electric field intensity at a particular point, what to do is you take a unit positive charge. Take a unit positive charge and keep that unit positive charge at a particular required point. Keep that unit positive charge at a particular required point. Suppose that point is at a distance r from the source charge. And as I already told you, source charge can be represented as Q0, and test charge you can take it as, now here the test charge is 1 coulomb positive charge. 1 coulomb positive charge. So you keep that 1 coulomb positive charge at a distance r from the source charge Q0. Are you getting my concept? You are having a source charge Q0 at a distance r from Q0, you want to find the electric field intensity. To find the electric field intensity, you keep a unit positive charge at that particular point. Okay, then you find out what is the force acting on that 1 coulomb positive charge placed at your required point. How you can find it out? You can find it out using Coulomb's law. What is the formula for finding the force using Coulomb's law? F is equal to 9 into 10 to the power 9 Q0 into 1 divided by R square. I repeat, F is equal to 9 into 10 to the power 9 into Q0 into 1 divided by R square. What is that? That is the force experienced by a unit positive charge placed at our required point, where we have to find out the electric field intensity. Are you getting? So, the force experienced by unit positive charge is defined as the field intensity at that particular point. Now you can recollect the gravitational field intensity that we have discussed in the last syllabus. While discussing the chapter gravitation and the gravitational field, I repeatedly told you that this concept we will repeat in next syllabus, that means 12th syllabus. So electric field intensity at a particular point, is defined as the force experienced by a unit positive charge placed at that particular point. Are you getting? I repeat, electric field intensity at a particular point is the force, electrostatic force experienced by a unit positive charge placed at that particular point. Okay, so that is electric field intensity. And suppose you have to find out the electric field intensity at a particular point due to a test charge Q0. What is the method? First of all, you find out where the required point, and you keep a unit positive charge at that particular required point, and find out what is the force acting on that unit positive charge placed at the particular point using Coulomb's law. That will be the electric field intensity at that particular point. Suppose you are not having such a unit positive charge. Instead of that, you are having a 10 coulomb positive charge. But you have to find out the field intensity at that particular point. What to do? Don't worry, you keep that 10 coulomb positive charge at that particular point. And then you find out what is the force acting on that 10 coulomb positive charge placed at that particular point. That you can do? Okay, that you can do. So find out the total force acting on the 10 coulomb positive charge placed at that particular point. Is it electric field intensity? Not at all. It is the force acting on 10 coulomb positive charge at that particular point. What is electric field intensity? Electric field intensity is the force acting on a unit positive charge placed at that particular point. How you can find out electric field intensity now? You just divide that force divided by the test charge. What is test charge? 10 coulomb positive charge. So when you are dividing that force with that 10 coulomb, then you are getting the force acting on unit positive charge. Is it okay? That is your electric field intensity at that particular point. So, definition for electric field intensity at a particular point is the force experienced by unit positive charge placed at that particular point. And what is the relation between electric field and electric force? Electric field means electric field intensity. Electric field intensity is the electric force experienced by unit positive charge. Are you getting it? Electric field intensity is the electric force experienced by unit positive charge placed at a particular point. I think it is clear. Unit positive charge is the test charge. And if it is instead of unit positive charge, you are having Q amount of test charge, using that to find out the electric field intensity due to a source charge Q0. Remember, test charge is Q and the source charge is Q0. Now you can find out the force acting on the force acting on the test charge Q due to the source charge Q0. What is that? F is equal to, yes, 1 by 4 pi epsilon 0 Q0 into Q divided by R square. What is that? That is the total electric force acting on the test charge Q. If you are defining that F divided by Q, the test charge, what you are getting? Electric field intensity. Is it okay? So, there is a relation between electric field intensity and electrostatic force. In words, I can tell you, electric field intensity is the electric force experienced by a unit positive charge placed at that particular point. Mathematically, we can say that electric force is denoted as F. Electric field intensity is denoted by capital E. Okay. So 4 notations you have to remember here. Note it down. 4 notations you have to remember here. What are those 4 notations? First one is Q0. What is Q0? Yes, it is source charge. And what is Q? Yes, that is the test charge. What is F? F is the total force acting on the test charge. And what is E? E is the electric field intensity. Note it down? Yes. Okay. Then E is equal to F divided by Q. E is equal to F divided by Q. What is E? Electric field intensity. What is F? Electrostatic force. And what is Q? What is Q? Yes, it is the test charge, not the source charge. Is it clear? So, electric force and electric field intensity are related as E is equal to F by Q. Always remember, Q is not the source charge, but it is the test charge. Okay. So here we have defined what is electric field, what are electric field lines, what are the properties of electric field lines, and what do you mean by electric field intensity, and how you can find out the electric field intensity. How you can find out the electric field intensity? To find out the electric field intensity, keep unit positive charge at the particular point and find out the total force acting on that particular unit positive charge at that particular point. That is the electric field intensity at that particular point due to the source charge. Always remember how to find out the electric field intensity at a particular point. But that is clear. Keep 1 coulomb positive charge at the required point. Find out the force acting on that 1 coulomb positive charge. That will be the electric field intensity at that particular point. Okay. So that is electric field and electric field intensity and electric field lines and their properties. So here we have defined what is charge and what are the methods to make a neutral body charged one, or how you can make a neutral body charged one, how they are interaction you can find using Coulomb's law, vector form of Coulomb's law, then how the interaction is possible, that is through electric field, what is electric field and what are the electric field lines and electric field intensity. Okay. Now already we have said that when we started electrostatics, already we have said that there are two types of charges, positive charge and negative charge. There are two types of charges, positive charge and negative charge. Suppose you have two charged bodies. And they are having equal but opposite charges, which means magnitude of their charges is same but their sign is different. We can call the amount q amount of charge both the particles are having, or both the bodies are having the same charge q, but one is positive and the other is negative. So two equal and oppositely charged particles, or simply we can say two equal and opposite charges. When these two charges, equal and opposite charges, kept very close to each other, when two equal and opposite charges kept very close to each other, that is a particular system of charges in electrostatics. That is a particular system of charges in electrostatics. We can call that system as an electric dipole. Note down, electric dipole. How you can define an electric dipole? An electric dipole is a system of charges which consists two equal and opposite charges separated by a very small distance. Two equal and opposite charges separated by a very small distance can be considered as an electric dipole. Okay, an electric dipole is a system of two equal and opposite charges separated by a very small distance. It is very important that the system consists two equal and opposite charges, and these two charges should separate by a very small distance. And there is a particular property of an electric dipole called electric dipole moment. Note it down. Electric dipole moment. Electric dipole moment of a electric dipole moment for an electric dipole can be measured. It is measured as the product of one of the charge and the separation between these two charges. Are you getting? Dipole moment can be measured as a product of one of the charge and the distance between these two charges. Is it clear? We have both the charges are equally magnitude. So that is why we are taking any of the charge. Electric dipole moment, to find out the electric dipole moment, you take any of the charge and you multiply with the separation between these two charges. And one more thing, the separation between the charges in a dipole is known as dipole length of a dipole. Length of the dipole is the separation between the two charges. Simple words, we can say that two equal and opposite charges separated by a very small distance is an electric dipole. Its electric dipole moment can be measured as the product of one of the charge and the dipole length. Product of the dipole length and one of the charge. Okay. So that is a particular kind of a electrostatic system in which two equal and opposite charges are separated by a very small distance, and their property is electric dipole moment, and it can be measured as the product of one of the charge and length of the dipole. So electric dipole moment depends upon two factors. What are they? Yes, the charge and length of the dipole. Because electric dipole moment is measured as the product of charge and the length of the dipole. So how you can increase the dipole moment of an electric dipole? Since it can depend upon two factors, or it depends upon two factors, the dipole length and the charge of the dipole. First method to increase the dipole moment is increase the charge of a dipole. Is it? Automatically, if you increase the charge of a dipole, automatically the dipole moment will increase. Is there another method? Yes, some of you are saying that there is another method also. What is that? Increase the length of the dipole. Is it? But I can say there are methods to increase the dipole moment of a dipole. One is increase the charge on the dipole, and the other is increase the charge on the dipole. Surprised? Yes, I know. The second method that I mentioned here, that is, there are two factors that can affect the dipole moment. First one is the charge and the other is length of the dipole. But by increasing the length of the dipole, you can't increase the dipole moment. What is the reason? The reason is there in the definition of electric dipole. What is electric dipole? It is a system of two equal and opposite charges separated by a very small distance. If you increase the distance between the charges, you can't consider them as a dipole. They will become two separate charges. Now it is clear. So, to increase the dipole moment of an electric dipole, there is only one method, that you can increase the charge on the dipole. Okay, so that is electric dipole. Electric dipole is a system of two equal and opposite charges separated by a very small distance. Electric dipole moment is the product of one of the charge and the length of the dipole. Okay, that's all for today. We will meet. Bye.